let's take a look at our bell ringer question. How many grams of potassium chlorate, or KClO3, will dissolve in 100 grams of water at 30 degrees Celsius? This is reviewing how to read a solubility curve graph. The point that you should be focusing on is right here. We know that we're looking for a temperature of 30 degrees. So we need to first locate our temperature on our x-axis. X-axis in this case tells us temperature. So we find 30 degrees. And then we go up to see where that meets our solubility curve. And this is the point right there where they meet. So then we go over and then we read our y-axis value, and our y-axis tells us grams of solute per 100 grams of water. So at 30 degrees, I have 10 grams of solute dissolved in 100 grams of water. So the answer to how many grams of potassium chlorate will dissolve in 100 grams of water at 30 degrees Celsius is 10 grams of potassium chlorate. Today, we're going to be talking about acids and bases. And our learning objectives are, I can describe what an acid is, I can describe what a base is, and using pH values, I can classify substances as acidic, neutral, or basic. So you've probably heard the terms acids and bases before, and you've maybe even talked about especially acids in your everyday life, because we use acids in acidity is a flavor that we use oftentimes, like when we're cooking. So perhaps you've heard of it before, but let's talk about the scientific definition of what an acid is. Acids are substances that lose hydrogen plus ions in solutions. So think back to when we talked about the formation of ions from an element. An ion forms when an element loses or gains an electron. Is a hydrogen plus ion an element that has lost or gained an electron? It has lost an electron. Remember, electrons have a charge of -1, and the protons in the nucleus have a charge of +1. So if we lose an electron, then we have more positive charge than we have negative charge in the remaining electrons. So we have an overall charge of +1. So acids are substances that have hydrogen in their chemical formulas, and those hydrogens kind of pop off, and they are ionized. That electron kind of stays behind. And those hydrogens react with different materials that are in those solutions. The properties of acids are that they are sour and they are corrosive. Corrosive means that they can kind of eat through, or they can damage the materials that they touch. So if we were in person and we were doing a lab with an acid, would you taste the acid to see if it was sour? You would not, because for one thing, it is corrosive. Acids are corrosive. And when we're in a chemistry lab, we don't taste things. We use a lot of our other senses. We can even use our sense of smell sometimes if we're really gentle and we waft scents, but we don't ever want to taste any chemicals that we're working with, because they might be dangerous to our mucous membranes in our mouth. So we have acids, which are substances that lose their hydrogen plus ions in solutions, and we have bases. And bases are substances that produce OH minus or hydroxide ions in solutions. So just like H plus is an ion because it's lost an electron, this is an oxygen and a hydrogen. And has it gained an electron or lost an electron? This ion has gained an electron because we have an overall charge of -1. So bases are substances that produce OH or hydroxide ions in solution. The properties of bases are that they are bitter. So again, if we were in a lab and we had an acid or we had a base, you wouldn't taste it, but if you did, it would be bitter. It's corrosive. So just like acids, it can damage, it can damage the materials it comes in contact with, and it's slippery in water. So as we'll see in just a second, a good example of a base is soap. When we put soap on our hands, it feels slippery in water, and a lot of other bases are similar in that sense, where when they mix with water in solution, they feel very slippery. If you've heard of acids and bases, you might also have heard of the pH scale. And the pH scale goes from 0 to 14, and it tells us how acidic, neutral, or basic different materials are. We use the different numbers, and we can use decimals as well to talk about how much or how great the concentration of hydrogen ions is in any given solution. So pH, you might be thinking this is a little strange because the more acidic things have smaller numbers and basic things have big numbers. But we're measuring the concentration of hydrogen ions, and we know that hydrogen ions are characteristic of acids. The pH scale is an inverse measure. So that means lower numbers mean higher volume or higher concentration of hydrogen ions. And big numbers on the basic side mean that these materials have very low concentrations of hydrogen ions. So it takes a little bit to get used to, but low numbers means high hydrogen ion concentration. High numbers means low hydrogen ion concentration. And that's basically how the pH scale works. But let's take a look at some of the materials on the pH scale. Right in the middle, dead center, neutral, is water. And this would be water that doesn't have any minerals or ions or anything in it. We go a little bit above, it says it's an 8, but it's actually like a 7.4. Our blood is slightly basic. It's a little bit higher, it has a higher number, which means it has a lower concentration of hydrogen ions, and it is slightly basic. If we go slightly below water, we have milk. Milk is slightly acidic. We might not think of it as something acidic, but it is more acidic. It has a higher concentration of hydrogen ions than water. If you look over at number 12, like I said, soap is basic. And even a little bit more basic than soap is bleach. If we jump down to our acid end, we can see at number 3, we've got vinegar. Number 2, we've got lemon juice. And number 1, we have stomach acid. So we've got quite a range of different materials, but all of them have different concentrations of hydrogen ions. The ones that have high concentrations of hydrogen ions have low pH values, and they are acidic. The middle values are neutral, and the high values have low concentrations of hydrogen ions, so they are basic. So like I said, the pH scale is how we measure acidity, basicity, and neutrality. But it's a pretty cool scale because in addition to being an inverse measure, so remember, low value means high concentration of hydrogen ions, it is also a scale that measures things in a base of 10. So that means that as I go from one unit to the next, if I go from 1 to 2, I'm not just increasing I'm not just doubling my acidity. I'm not going from 1 to 2 and just adding a one increase. I'm actually increasing or decreasing my acidity by 10. So remember, 1 is more acidic than 2 on the pH scale. So 1 is 10 times more acidic than a pH of 2. And a pH of 2 is 10 times more acidic than a pH of 3. And so on and so forth. A pH of 13 is 10 times less basic than a pH of 14. So that's pretty crazy. If we go up one number on the pH scale, we're decreasing our acidity or increasing our basicity, depending on which end of the pH scale we're on, by a factor of 10. So that's why when we looked at that last slide where we had the all of the different materials and their pH values on it, bleach was only one number higher than hand soap. Bleach is something that we wouldn't use on our hands. That would be very, very aggressive and probably corrosive and damaging to our hands. But it's only one number higher, but one pH unit is 10 times more basic than the pH unit before it. There are a couple of different ways that we can measure pH. So if you've ever swum in a pool that has chlorine, oftentimes we need to use some sort of indicator to measure what the pH levels are in that pool water to see if we need to add any more chemicals to balance it out, or if we need to add something else to make it more acidic, more basic. And we use something called an indicator. And an indicator is a compound that changes color at different pH values when it reacts with acidic or basic compounds. And a really good example of this is bromothiol blue. As you can see, as you can probably guess from the name, it's actually a blue liquid. And when we put it in different solutions that have different acidities, it turns different colors. So you can see at an acidity of 5.5, it's almost a yellow color. At an acidity of 6.0, it's still pretty yellow, but it's getting a little tiny bit green. At 6.5, it gets pretty green. At 7, an acidity of 7, so neutral, it's kind of a greeny, almost a little bit blue, but pretty green. And then 7.5, pretty blue, and then at 8, very blue. So each of those are different liquids with different pH values. When we add the bromothiol blue to the liquid, the bromothiol blue changes color, and then we would compare that to a standard. So something like this, like a picture, that would say that this color of liquid means that we have this value of a pH.